Okay, so okay, let's wait for just one more minute, and then we will continue our class. Okay, so let's start the course. Previously, we have this project. We're writing another way, which is neat. We have separate shaders, we have separate shader files, and it looks great. And we can draw this triangle. Now we want to add some more colors. Because here, you see this triangle is almost orange, but all the triangle is orange. Now we want to make each vertex with different color. And let's see what will happen. So first, let's look at here. This is our position, right? We can make some notes. Says this is position. Now let's add some color here. And we want to add a color for each vertex. And the color is just one attribute for the vertices. So if you want to add some colors, you need to pass it to the graphic memory together with the position. So let's do something like this. Let's add red for the first for these points or vertices, and let's add green for this one. But not let's add blue for last point. First, let's add this. And we will see how it looks like now. Because now we have the chance to see more than just one color. And in fact, there's some basic theory behind it and mathematics things behind it. Okay, so these are just colors. This is red, green, and blue. Because color has 3 components. I mean, if you have alpha, it's 4 components. The red is 8-bit, green is 8-bit, and blue is 8-bit. So this one has only red component, which is stand for red. This is green and blue. Now, in order to make it readable, first, let's see our code here. There's something we need to change now. Because here, for the vertices, we have a lot of data. And if you go here and read this line, check all these parameters. So this is for location equals to 0, right? And for 3 float number, which is 1 position, and we don't normalize it, and we start from the beginning, and we jump 3 float number to get the next one. But now it seems different, because if we jump 3 position, 3 float number, we come here, and this is color. This is not the second position, right? So here we need to change this to 6. So 6 position, 6 float number to get the next position. Okay, so get it? This part is for this. How far away we want to get the second position. So 6. But how to read the color? Let's check the vertex shader. We don't allow the vertex shader to read the colors, because now we only have 1 input. In order to have second input, which stands for color, we need a more layout for the location equals to 1 in Week3 color. Now we have chance to read the color, right? This is the color. And location 1 means, okay, we can set the VAO, vertex array object, to bind with this color. But how to bind the color? Let's go back to the main function. here, this is the function we use to set the attribute. And we set it for location 0. Because location 0 means the position, right? In order to read the color, we need to set one more line, one more attribute for the color. So let's copy this code and paste it. And we put 1, 1 here. Okay, so let's see all these parameters. Do we need to change something here? I mean, first you think about that. Do we need to change something here? And if yes, which one we might need to change? So first thing, this is for location 0 and this is for location 1. So we are setting this line for the location 1, I mean for the color variable. Okay, yeah, this one. Because if we want to get the first color, we should start from here, right? Not from the beginning. We go for 6 different float number to get the second color. So this is the starting position. But now the starting position is still 0. We need to modify it here. And the modification is 3 times size of GR float. So now we can read the colors. I mean, the color has been transferred to the graphic memory together with the positions using this GR buffer data function. So by using GR buffer data, we can transfer all this data to the graphic memory. And you see, we set this line, this 2 function, for position, so we can read the position. But then we set this function, 2 function, to read the color. We can read the color using this 2. Why was that? Because this thing, the first parameter, 0 and 1, they are linked to the locations in our vertex shader. So if you set 0, it means you set something for location equals to 0. It means set this variable. If you set this, it means you are setting this. Now we have the color. But now at this time, color is in vertex shader. The shader which handles the color is in the fragment. So how we do that? Let's say it in this way. So this is a vertex shader, this is a fragment shader. You see, only the fragment shader handles the color, not the vertex shader. Vertex shader only handles the position. So in order to do that, we need to output the color to our fragment shader. The way to output our color is first we indicate its out, which output, and give another variable name, which is different from this, because this is read through the graphic memory. And once we did this, we need to copy the code and paste it here. We need an in. Why we need to copy and paste here? Because the data variable, data type, and the variable name should be identical. Okay? So in order you make the right thing, copy and paste is the best choice. You only change out and in. Okay? And then to parsing this our color, we only do something like our color equals to color. And here, now we can use this color. We can use our color. Color equals Week4 our color 1.0f. Okay. So this is the code that we use to have different color for different vertices. And the rest of the code don't need to change because we still draw only 3 points for one triangle. Let's run the code and see if everything's right. Yeah, we have this. If you saw this triangle, each vertex is with different color, then it is right. I mean, you might doubt why it have this color inside of this triangle. I mean, this is done by rasterization or interpolation. And that's the thing we will go through for today's lecture. I mean, what's the basic theory and the mathematics things behind it. So first make the code right, and then we will see some slides and some mathematical functions about how we get this. So I will give you just a few more minutes to make sure you change the vertex, all the shaders. Okay, make all the shaders right. If everything's right, you should be able to run the code and solve this triangle. Okay, so let's see some background theory behind it. So why we have this triangle? So the first thing we need to cover is screen coordinates. We draw a triangle within the window, right? Actually, it's on the screen. And the triangle is defined by 3 points, the x, y, and z. We have our 3 coordinates for each point, and each coordinate has 3 parts, or 3 components. So if you check with our code, you will see we have all these coordinates. But how the coordinate looks like? This is screen coordinates. Because we draw the thing directly on the screen, we should everything we provide within the screen coordinates. So the screen coordinates looks like this. Okay? So the horizontal line is the x, and the vertical line is y. And there's the z-axis, the z-axis. Z-axis is from the screen, point towards you. So this is z-axis. We have 3 axes. And the range of this axis is from -1 to 1. -1 to 1. So let's check our points. This is screen coordinates, right? We provide 3 points. This one, and this one. If you check the code, you will see we provided all these 3 points. And that component is 0, 0, 0.0. So that's on the same plane. So this explains why we have this triangle. This is the coordinate we provide. Just check on this part, all the coordinates are negative. This is positive, negative. This area is positive, positive. Okay? So this is the coordinates. So, but now you only see these 3 points, right? I mean 3 vertices. What about the points within this triangle? How we decide it? And how do we interpolate it? I mean, this is the key. And there are a lot of mathematics behind it. And then today we will see some of them. Okay. We will see how we interpolate and why it was like this. First, let's see this. Because triangle in both 2D and 3D are the fundamental modeling primitives in many graphic programs. We have seen this. You remember in the first class when I show you how to use the Unreal Engine. I draw everything, right? I draw everything. I show you one cube. For the cube, I use the brush and the wire framework. So you see how everything has some basic shape, which is triangle. So triangle is the fundamental modeling for all computer graphic programs. I mean, almost every computer graphic programs. And all the information, such as color, is tagged onto triangle vertices. But within the triangle, this information is interpolated across the triangle. Okay, So everything within the triangle should be interpolated. And the way to interpolate this triangle is called the biocentric coordinates. So what is biocentric coordinates? Biocentric coordinates is a special kind of coordinate system. We interpolate this. We use this coordinate system in this way. So first, let's look at the ordinary coordinate system. You might have known some ordinary coordinate system before in mathematics and maybe in some other mathematics course, right? The general coordinate system has one orange point, which is 0. Here we have an orange point, which is A, well, which is almost identical. And for the ordinary coordinate system, all the axes should be perpendicular to each other, right? So for example, if this x and y should be perpendicular to each other. And the basic unit, the unit length of all the axes should be the same. Should be identical. That is the ordinary coordinate system. But the bicentric coordinate system is different. We still have an origin point, but the axes could not be perpendicular. We don't have this requirement. This is not a must. The axes can be not perpendicular to each other. So we can have some other angles here. So for example, on this figure, you see these two axes, they are not perpendicular to each other. They have some angles here. And the length, the unit length is also different. So for here, the BA vector, the length of BA vector is not equal to the length of CA vector. We use this to create some coordinate system, which we call it barycentric coordinates. And now, every point P in this space, this is a 2D space, every point P in this space can be described using this. We have two parameters, two coefficients here, and by grouping all this together, we can get the point P. So it means every point on this plane can be categorized by this function. So why we use that? Because makes problem simple. Let's see here. So first, we reorder the terms in this equation, and we get this. And we redefine a new variable which is called alpha. Alpha equals to 1 minus beta minus gamma. Oh, I think this is lambda? Yeah, it should be lambda. And it has some constraints. First, we say, okay, every point P is a function of these three variables, and these three variables, they have a constraint, which means, if we add them together, it should be equal to 1. So, now if we have all these three variables, if we calculate all these three variables, and we see some interesting things. First, if all the points, if one point satisfies above constraint, we calculate the alpha, beta, and I think this should be, I think this is a gamma. I can't remember. But if we calculate all these three variables for one point, and all of these three variables satisfies above constraints, here, this point is in the triangle. That's an interesting thing. If we calculate that, we will find, okay, everything is inside of this, the points is inside of the triangle. And we use the same rules and find if one coordinate is 0 and two others satisfy this, then it is on the edge. Finally, if two are 0 and the rest is 1, it is on the vertices. So that's the cool thing. We transfer the problem of finding if a point is within the triangle or not to the form that we just solve these three variables and check if they satisfy this constraint. This is a great progress, because now we simplify the problem. Okay. So next, how to calculate this? Given point P, we can regroup this function, the linear function, and solve it, just using this way. This is a linear function. We have learned how to solve it, both in high school mathematics and in linear algebra. Both these two courses, we have learned how to solve it. By solving this, we can get beta, gamma, and alpha. And we check if it satisfies the rules within this page. But the thing is, calculate this in computer is very difficult. It is straightforward if you just do it by hand, but within the computer it's different. It's very difficult. So, within the computer, we find a new way to calculate. We use the distance. First, let's see how we define the distance to a line for a point. If a point is here, the distance from the point to the line is defined by this. It's given by this. So FAB means we put the AB, the points, to our line function and divide it by the coefficient of the line function. The line function is this. Then we find there is an easy way to calculate the coefficient. For example, the beta. We can do this by just calculate the distance of this x, y, or the P points to the line AC and compare it to the point, to the distance of the point to line AC. So we just calculate this ratio. So for example, P is here. If P is here, we calculate this distance, and we calculate the distance between B and AC. So we compare it, and this ratio is beta. If beta is smaller than 1, then it has a great potential that it might be within the triangle. So this is the way we calculate this. And by doing this, we simplify the distance function because we do not need to divide the square root of a squared plus b squared, right? Because we can ignore that. And this becomes very, very easy because beta, we can solve beta by using just, we can solve this by just 2 times and 2 addition. 2 multiply with 2 addition, we get this, and 2 multiply and 2 addition, we have this, and then we divide it. This time we have beta. So we can extend it by from the distance to the square, to the area of the triangle. Because they share the same edge. For example, for the AC, the edge AC is the same. So the distance from point to this edge is equal to the distance or the area ratio of this triangle. Right? You get it? So this is the easy way to calculate the ratio. And now we change calculating this coefficient from the distance to the area. So this extension is extremely useful for 3D area because 3D area, the area of a triangle can be calculated as the determinant of this matrix. Okay? So for 2D is this, and for 3D, we just add one more line and one more column. And the geometric meaning is slightly changed. It changed from area to something more like the volume. But the basic idea is the same. Now for 3D space, we can use this function. We still can have this P point, which is a combination of point A, B, and C. It's the same. We have surface normal. And now we can easily calculate alpha, beta, and lambda using this function. And this function is simple. We only use this to get it. Okay? So this is the mathematical background behind everything. So with this, we can have this colorful triangle. And we know why it has so many different colors within the triangle. Because next time, if you want to see the color within the triangle, you need to calculate alpha, beta, and gamma, and the lambda here. They are all calculated by hardware, so you don't need to worry about how to calculate them, because they are all done automatically. You don't need to do it by yourself. Okay, so let's have a break, and we will go through something else. Okay, so let's come back. Now we have seen the theory behind it, behind our code. We know how the triangle is calculated, right? But we want to do something more. We want to draw something rather than triangle. What if we draw something more than just one triangle? Let's see. If we want to draw two triangles, what to do? Actually, if we want to draw a square. Let's see the code. This is for triangle, right? Let's comment out. Now we want to draw a rectangle. We want to draw a red rectangle. So let's first give these coordinates of this rectangle. So actually, it's two triangles. So it's the first triangle and second triangle. If we want to draw a square, actually what we did is drawing two triangles. So let's give it a position for these two triangles. Now the first triangle, we want to draw to right one. So the first, we still have the position. So it's 0.5, 0.5 F, point. And we want to have the color, which is just red. Okay? So this is for position, and this is for color. So next position is this. And the color is still red. Last one is so actually this is top right. Right? This is, let's see, bottom right. This one is top left. So this is the first triangle. You see this, the vertex coordinates is slightly different from the previous one. And let's do the second one. And together with the color. Bottom right. Bottom left. And top left. Okay? I suppose most of you should finish this. Then, there's only one thing we need to change. Because now we are drawing 6 points. What we need to do here is only change this to 6. So we not draw the triangle, but we draw 6 points. Because we need to draw 2 triangles. Then we run the code. There should be a red square or red rectangle because the window is not square. So you should be able to draw this. Next, I will give you the second homework. Now we will have the second homework. First, I will use the the Unreal Engine to show what I want. Show the effect. Then you can see how this was built step by step. Okay, so you can simulate these things, but you need to write it in OpenGL. So implement this function here. So I will open the Unreal Engine and then show you what I want. This is a very common function we use for Unreal. Homework? Yeah. So I will create something for the homework. I will create a material. And within this material, what I want is each of you to implement this. First, we have to what is red, what is green. And we have a function points sine function, and we have something more like sine function is from minus 1 to 1. So we add 1 to this from 0 to t divided by 0.5. Then we have a linear calculation. If we combine these two, and these two, together. We use this to assign the color. Let's apply it. So if you check, this is basically the steps. Okay, never mind. So I think my voice is going back to normal now. You should be able to hear me now. I mean, those. I just show you what I want in the Unreal Engine. Yeah, you should do it by typing, and I will give you a hint about how to do it. You see, this is our code, right? Oh, sorry, no, this is not our code. Let's open it. This is our code. The only thing we don't know is how to have the time and make the time inside of our shader, right? Because you see, the color is changing within the shader. Only the fragment shader determine how we change, what kind of color we draw. So first, we need to get the time. In order to get the time, we can have this function, float time equals to grfw get time. Now we get the time. You see, when I did this, I used time and get the sine value of the time and modify it to make it range from 0 to 1, and then use a linear interpolation, right? So this time is determining the weight of two colors. So that's what you need to do. So time. But then how to make this time inside of the shader? First, we get the time here, right? This is the way we get the time. On the inside shader, how we did this? We have one thing called the uniform float time. And to read this time, now we have this time in the fragment shader. But how to assign the value for the time? We did it in this way. After the shader, we say gl uniform 1f gl get uniform location. And this is shader program. Sorry, it's our shader. Our shader, the program. And then we sign it with the value. First, we need to find the variable, and then we get. Sorry, it's this time, and we sign it with time. So this is the way we get the time from the system and passing the time to our fragment shader. Now within the fragment shader, you can use this time to change the weight of some mix function. If you can't open this, just check if your structure is right. In order to open this two file, you need to provide the right path. This is the right path. It means you should go to this folder and okay, let's show you in this way. So this is a file structure. And this is the function for this function. You might have the same name like main.cpp or console application cpp or some learn or first try or test cpp, any type kind of cpp. And under this level, within the folder, there should be another folder called res. I mean, if you open this file, and this within the res, there's the shaders. And check this is the same with this structure. So res means, okay, first on this level, let me find a folder called res. Then this means go into it, find a folder called shaders. So here is the shaders, and get into it, and get core.vs. So this is the same. I mean, so if your code doesn't work, it might be because you provide the right data structure for the folder. Check within this folder. Not check inside the Visual Studio, just check the folder. And see if you make it in the right way. In that case, just show me how what it said within the red window. Sorry, the black window. Take a screenshot and show me what's in the black window. Okay. And when you run the code, show me what's in the black window. I mean, when you run the code, just show me two windows pop up, right? One is black, one is the window we draw. Show me the other one. There's one possibility. Do not type the backslash before res. Okay, just like this. Sometimes some students just make a mistake, type something before res. I mean, this homework is left for you for the holiday, so you can finish that within the holiday. And after that, we need to check the homework. The way we need to check homework, the way we check homework is we will open some Tencent meeting. Within the meeting, we can share the screen. So each of you share the screen, and then I will see what's going. Yes, you got it. So what's wrong here? I saw this triangle. What's the problem? I mean, what's your question? I can see this window. It seems that it works. Yes, the same code with the first one, but with different. Then we modify it a little bit to draw a rectangle. I mean, and the red square. We make it a red square. So make sure you can draw this red square. What do you mean you can't open this two file? I didn't get it. Just drag it to this Visual Studio, and you can open it. Do you mean how to open it? For Visual Studio, just drag this. For example, drag code.vs and drag it to the Visual Studio, and then you open it. For the code VS and code FS, for this course, it looks like this. So this is code VS, and this is code FS. Yes, just drag it into it. Okay, so the class is over for today. If you still have questions, I'm still here. I will still be here to solving all the problems, all the questions. If you don't have any question, the class is over, but I'm still here. Okay, just let you know. I will be here for like 10 or 20 minutes, unless you don't have any questions.